The purpose of this one is to work more on functions, especially composite functions. Now you've dealt with function notation before, and we've already been dealing with this for a bit too. Let's just take a look at here. We have h of g of f of 2. So what we're going to do is just deal with the innermost function first. H of g f of 2 will be 3 times 2 minus 2. So we have h of g of 6 minus 2, or 4. What is g of 4? G of 4 would be 4 squared, or h of 16. And then we take the square root of that, and we get 4. Does it matter if you switch the order? Let's take a look. H of f of, this time g is our innermost function, so we have 2 squared. So we have h of f of 4. Now we need to plug in 4 into the x spot of f. So h of 3 times 4 minus 2. So 12 minus 2 is 10. H of 10, the square root of 10. So does order matter here? Yes, absolutely it does. Write this equation here as a composite of functions using f, g, and or h. What we need to do is we need to examine these three things and look and see how they work together to create this equation. So we want to focus on the inside part. We look here and we see that this is 3 times x squared minus 2. Well, that's very similar to 3x minus 2, except instead of this x, we have x squared. If we're taking a look over here, we see x squared. So in other words, if x squared is plugged into this x spot, or in other words, if we had f of x squared, we would get 3x squared minus 2. So if we had that, f of x squared would be 3 times x squared minus 2. Now we want all of that to be plugged inside the square root. So in other words, this has to go inside the h spot, or the x in as far as that function goes, inside the x. And now what is x squared? X squared is our g. So we have f of g of x. That gives us our 3x squared minus 2, and we want that all plugged into h. And so y equals h of f of g of x. Which of the is a function and which is not? Y. Let's take a quick look at a sketch of this. Parabola opens up. Is that a function? Yes. Y, for every x, there is one y value. You could also talk about passing that vertical line test. This is a definition we had before. X equals y squared. What does that graph look like? Well, that's very similar, except x and y are switched here. That is looking like here. One way you could do it is, if you didn't know this right away, if you solved for y, you would get plus or minus the square root of x. Well, here's the positive square root of x, and then the negative is right below, negative root x. Or this is just a parabola that opens up to the right. Let's look at the next one. We have number 5. F of g of x is going to be f of 1 over x minus 5. So we'll plug in that into the square root. So we have the square root of 1 over x minus 5. And for right now, we're still rationalizing things, although we do have to be careful about that. When we multiply by root x minus 5 over root x minus 5, we get root x minus 5 over the quantity x minus 5. Now it says to state the domain. We can look at this. There's a couple things going on. Number one, we have a square root, and remember what we did before. we have a square root, and we have to take everything in the square root, and we have to make that greater than or equal to 0. But we also have this x minus 5 in the bottom, which says x minus 5 cannot equal 0. How could we combine these two together? We could just say x minus 5 is strictly greater than 0. Or in other words, x is greater than 5. And that could have been done right here. We could say, well, I have this thing. I know it's going to have to be positive. And we'll end up getting x. That would mean this denominator for this type of problem, the x minus 5 is greater than 0. So there is our domain, and we'd write x such that x is greater than 5. Let's look at g of f of x. Now we have g of f of x, and that's the square root of x. So we have 1 over, plug in the square root of x for our x spot. Now how do we rationalize this one? This one we're going to multiply by the conjugate idea. So we get the square root of x plus 5 over x minus 25. One thing I didn't mention over here, and I probably should, is I did not take into account immediately, since we're finding the domain of this composite function, we need to also take into account that x cannot equal 5 in the original. But that was taken care of because we still have x minus 5 in the denominator. Over here we have, in the inside function, that domain is x has to be greater than or equal to 0. We still have that in this one as well. Is there anything else in this problem? Well, we can't have the denominator equal to 0, so x minus 25 cannot equal 0. So we get x cannot equal 25. Now we just need to put those together. So we'll say the domain is all values of x such that x is greater than or equal to 0 and x cannot equal 25. So it's where those things overlap. It's also possible to say between including 0, between 0 and 25, not including 25, and then greater than 25. Or we could just write it like this. Let's look at our next problem. And it looks like I have a little typo on this one, that this should be problem number 6 and 7. I'll fix it for the sheet that you have. All right, find the area and perimeter. So here, what we're going to do is the area is a circle. The area of a circle is pi r squared, but we have a semicircle here for this area. So we are going to say area of the semicircle equals 1/2 of pi r squared. What about the perimeter? What is perimeter? Perimeter is all the outside lengths added up. So what we have here is 1/2 of the circumference. Recall that the circumference of a circle is pi 2 pi r, or you could say pi times the diameter. But do we want all of that? No, we only want 1/2 of it here. So we're going to have just 1/2. And will this make up the entire perimeter? Not exactly. We also need to take into account this bottom piece. So we'll have the perimeter in terms of r will be just pi r, because it's 1/2 of 2 pi r, plus 2 radii. Now let's write the area as a function of perimeter. So we know we have that equation, area equals pi r squared. Right now, it's in terms of r. We have r, and we want p. What this tells us is we need an equation to relate r and p. Do we have any? Well, yes we do. Put that There, we have it right here. So what does that mean? That means we have this equation. We need to get rid of, we want to get rid of r and replace it with p and other numbers, whatever they may be. So in other words, what this is telling us, we need to solve for r in the p equation. So we take this and we have p equals, now how do we deal with this? We have pi r and 2r. We need to get 1r so we can solve for it. So we need to have just 1r on this side, factor it. So we have pi plus 2, so r is p over pi plus 2. Now we can take that and come back to our equation here, our r, that's the same thing, and we will have a equals pi times the quantity of p over pi plus 2, and all of that is being squared. And we can write that as, oh, I was just thinking I forgot to put my 1/2 in there. So we have pi over 2 times p squared over pi plus 2 quantity squared. Next one. This one should be pretty straightforward. This is just another one. You'll see examples of this. We have f of x, so we're just going to plug in f of x inside. And now we have 2 times 2x minus 1, subtracting 1, 4x minus 2 minus 1, so we get 4x minus 3. Now when we do that, we're going to do the exact same thing again here. This is f of 2x minus 1, and since we just did that, I'm not going to redo it. I'll just put in 4x minus 3. Now it's 2 times the quantity of 4x minus 3, all minus 1. So I have 8x minus 6 minus 1, or 8x minus 7. And one more example in terms of looking around and seeing how do you create this expression using these 3 functions. We have 2 times the square root of x, so however, and then minus 1. However we get that 2 and the 1, we'll have to look, but the square root of x is going to be plugged into it. How can we get 2 times something minus 1? Over here we have 6 times x minus 3. What could we do to that to get the 2 times something minus 1? We're going to divide each one of them by 3. Well, that's what's happening here. So if we had 6x minus 3 over 3, we would end up getting our 2x minus 1. So in other words, instead of this x for the h, we want to plug in g. So this would be h of g of x. Now what do we want? We want to plug the f into this spot right there. So in other words, we want that square root of x to go on the inside instead of having this x there. We're going to have h of g of f of x and so just to check it, we would have h of g of square root of x, which would be h of 6 root x minus 3, which would be 6 root x minus 3, all divided by 3, and that'll give us 2 root x minus 1. And that's it for the composite functions.